Welcome to Happy Path Programming. I'm Bruce Eckel.
I'm James Ward. Well, today we have with us friend Paul Snively, and so glad to have you because I've really been
Thank
missing you over
Thanks.
the
I
last
appreciate
couple of
that.
years. I used to see you at conferences, and
Right.
you used to chime in on Twitter threads and provide so much wisdom. And
thank you.
I obviously we haven't been to conferences, and you dropped off Twitter, and so I've been missing you. So
Yeah,
good to have
I
you
appreciate that.
on our podcast.
Yeah, thank you. Yeah. I have taken a leave of absence from social media to a considerable extent.
Probably a good thing. Probably a healthy way to live.
It's certainly good for my mental health. So you guys are in Crested Butte, I guess.
We are.
And a few years back now, I moved to the Asheville, North Carolina area.
Oh, nice.
So I'm
as well.
Yeah, that's right. The Blue Ridge Mountains and all that good stuff. Yeah. So I don't know. I'm having said that now, I'm being encouraged from multiple sources to sort of get back into the conference game. And I was going to actually not presenting necessarily, but I certainly intended to attend LambdaConf 2019, I guess. And that would have been, as it turns out, had it happened, an opportunity to get back together with Amanda Locker, who we were just talking about because of our work on our presentations at Strange Loop all those years ago, 2012 and 2014.
Yeah. Which, for anyone that hasn't seen those presentations, they are both amazing. So there's types over test. What's that?
Types versus tests.
Types versus
was the
test.
first one. Yeah.
Yeah. And then what was the second one called?
Type systems: the good, the bad, and the ugly.
Right. Yeah.
We tried to be intellectually honest about, because we're both known as pretty heavyweight type mavens, and we tried to be intellectually honest about the fact that the type systems that most people are familiar with are not kind of the type systems we're talking about when we talk about why we like type systems. As a Scala developer, I think, and with a Scala audience, it's probably clearer that that's the case. That Scala's type system in particular is quite a bit more powerful than many others. So maybe that argument is not one that needs to be made to your audience.
It is interesting. You often see in the arguments around type systems where all the arguments against them are really coming from bad type systems.
Mm-hmm. Yeah, which you need to understand. I mean, this because my experience was I started with pre-ANSI C, which was not. I mean, even as limited typing that C has, it didn't have that. It was just basically seriously a high-level assembly language. Right. And then when we started using C++ and it would find all these issues because of the type system, it was like, oh, this is wonderful. And then, Java with its onerous bad syntax and type system and, oh my gosh. But it took me a long time to understand that was because Java was badly designed. And then when you see something that isn't intrusive, like Scala, where it's like, no, it's helping. That's the thing. I think for me, it was
the type system there to help you or help the compiler.
Right. When you're having to help the compiler and it's intrusive and it makes you type a bunch of things to do it.
And it doesn't let you express intent.
Mm-hmm. Exactly.
Is it a design tool for your application? I think you alluded to the feedback that I've heard most often, certainly, which is just, well, I'm only doing all this type ceremony to satisfy the compiler. And that's a valid criticism. That's a valid concern for sure that, I'm having to spell all this out multiple times. I mean, I think
That's right. You have to do it on the left side and on the right side.
Right, exactly. Yeah. Foo : uppercase foo equals new foo. Yeah, it was like, oh my goodness, how did, in what way have I offended God that we wound up here,
and it's just bad language design.
It fits into a paradigm that was dominant at the time. And I think another thing, and I don't know how much of Java's design reflects this, but I do think it's important to remember that Java was originally intended as a small embeddable language for set-top boxes. That was the target for the Oak project.
Well, that's how it started.
Right.
But
Right.
then the internet came along and they said, "Oh, we got to be the language of the internet." And
right.
also, it's important to understand that it was intended to be small talk.
Right. Yes. So it has that schizophrenia, right? It has the late binding of small talk, but it has the syntax of C++, and so it's kind of this neither fish nor fowl thing, and always kind of was. Never mind the challenge inherent in, for example, remember the old days when the JVM was literally baked into Netscape, for example,
right,
to run applets,
Yeah.
And sort of the uncomfortable marriage that was, because if you wrote applets, and I did, by the way, oh, that's actually a funny little piece of personal history. I worked for a consultancy in Hollywood that was doing promotional sites for some of the studios, one of which was Universal. And so I wound up doing a little graphical adventure game to go with a promotional site for a little Peter Jackson film, The Frighteners.
That's cool. Right. I remember that.
So on the website at the time, it would launch an applet that was some fun little.
Yeah.
And you know that in Java 17, they're removing the applet API.
At long last.
At long last.
Free at last.
Nobody's using it.
Yeah, or nobody's using it anymore.
Oh, your promotion.
Anyway, we can go back and forth over that history and take up all of our time. But
so what do you think was the kind of forcing ideas behind those earlier type systems that shaped it?
Well, I mean, I don't know about anybody else, but for me, the big intellectual leap, which thankfully came when I was about 16, 17, 18, certainly by the time I got to university, and I'll come back to that in a minute. But the big leap, I think, was going from the concept of types as describing how bits are laid out in memory, which is, obviously the C model, right? C and C++ model to a considerable extent. C++ goes beyond that, and I'll come back to that too. But once you start thinking of types as defining legal operations on values, defining legal operations on terms, then I think, for me, that's the opening of 2001: A Space Odyssey, after the monolith has taught the primates how to use tools, right? I mean, it's
that foundation.
Yeah, it's just this huge mental leap to go from types as descriptive, right? I mean, here's memory, here's a set of ones and zeros in memory, and you slap a type on that, and congratulations, you've got a description of how those ones and zeros are laid out. To no, actually, when you have this type, you've got a m by n matrix that you can multiply with some other m by n matrix, and things like that. And then to discover some of the languages that are really based on this idea. So the standard MLs and the OCamls and the Haskells and then ultimately Scala. But it can take a while to get there, and I certainly took a detour. I didn't get to types right away. So I'm from Indiana. I was born and raised in Indiana. So I went to Indiana University. In the mid-1980s. So there's Douglas Hofstadter, 2 years after winning the Pulitzer Prize for Gödel, Escher, Bach. There's Dan Friedman, the author of The Little Lisper, The Little Schemer. And I am. And in fact, I started reading The Little Lisper, which is what it was still called at the time, when I was still in high school. I actually found it in the Indiana University Library when I was there visiting while I was still in high school. So I got to IU, and you can just imagine, if you can imagine a very curious, maybe a little bright, certainly brash, arrogant 18-year-old running around with his copies of Gödel, Escher, Bach, and The Little Lisper, and running over to Lindley Hall and going, Dr. Hofstadter, Dr. Friedman, could you please explain, And they were ridiculously patient with me, which was a blessing. And then fast forward again to Strange Loop. I think it was the 2014 one where Dan Friedman, here I am presenting at the same conference as Dan Friedman. And then I'm sitting in the Union Station bar after one of the days, and I'm just wiped. I am completely wiped out. Maybe even after our presentation, after Amanda's in my presentation, and I'm sitting there all by myself. And then Amanda wanders over with Dr. Friedman and sits us down. And the next thing I know, I'm getting a manuscript copy of The Little Prover, which I wound up reviewing. So that was a great honor, and really enjoyed that. So anyway, you don't go to IU in the mid '80s and study with Dr. Friedman and Dr. Hofstadter and come away not knowing skiing. so I went through the whole, and I was interested in artificial intelligence and all that kind of stuff anyway. So I went through this big Lisp phase. That went on for a decade and a half or more, to such an extent that I also wound up reviewing Peter Norvig's Paradigms of Artificial Intelligence Programming for Morgan Kaufman. What was that, 90, 91, something like that. So I was a big Lisp fan. So when it comes to functional programming, I was there, right? I mean, certainly from the...
You were there 40 years ago.
I was there. I was into functional programming before it was cool.
Yeah.
But it was
a functional programming hipster.
Exactly. And I've got the beard to prove it. But it was all dynamically typed. And I bought into the argument that was liberating, right? I mean, again, compared to the type systems that we had with Pascal or C or, what have you, in those days. But then, I discovered OCaml in the mid 90s, and I came across some academic stuff about proving properties of communication protocols, networking protocols, that kind of stuff with proof assistants that were based on type theory and all this kind of stuff. And it was one of those situations. I don't know if you guys have ever been in exactly this position, but the thought that literally ran through my head was, it's not acceptable for me not to understand this. It's like, okay, and the technical term for that, by the way, is obsession. So there I was, coming with this massive Lisp background and all this kind of stuff, and being faced with all this kind of, not only are types something you can use in your programming to, manage the layout of bits in memory, or even just manage legal operations on values, but there's actually a relationship to formal logic there. And then you poke at that a little bit, and that ball of yarn unwinds to the Curry-Howard isomorphism and proof assistance and, dependently typed programming languages. And, it's a floor topping. No, it's a dessert wax. It's, so you look at Agda or Idris or Coq, the proof assistant, the French proof assistant. And it's like, yeah, these are programming languages. These are purely functional programming languages with unbelievably powerful type systems. And then you start looking towards the future, and it's like, well, okay, is this stuff ever going to hit the mainstream? We have enough of a challenge talking about Scala and talking about Haskell, talking about purely functional programming with type systems that are considered very sophisticated and very complex today. And then there's this whole other world, that we haven't quite gotten to yet.
But Scala seems to be bridging those ideas to the mainstream in a pretty big way.
I think so.
Even like Kotlin has embraced a lot of these things as well.
With the Arrow library.
Yeah, with Arrow.
Yeah. That's really good work. Did that come out of, refresh my memory, is that 47 Degrees?
Yep, that's 47 Degrees.
That did it. Yeah. I worked with some of the 47 Degrees guys while they were working on Arrow for Kotlin. I think there's a lot of overlap between some libraries that they did for Scala and Arrow. In particular, I think their distributed procedure call or remote procedure call library, Mu, came out of sort of the intersection of both of those projects. Really, really good and interesting work. And they certainly have pushed Kotlin a lot farther than I thought Kotlin could go as far as its type system is concerned, to be honest, and I think that's great. It's funny if you look at the expressive power of type systems, which I guess is sort of what we're touching on here. there has been a stunning amount of progress. And, it's funny. I think now one of my favorite examples of that is TypeScript. And that's because I think because it had the design goal of supporting JavaScript as is, any valid JavaScript program is a valid TypeScript program. And it wants to be able to provide typings for existing JavaScript libraries. So it's not just for new code. Its type system had to just become ridiculously sophisticated because of all the JavaScript idioms that don't fit neatly into the dominant type system paradigms. You have to. So, for example, it's a common JavaScript thing to say, we'll take a parameter. We'll have a function that can take a parameter. It's going to be a string, but it's going to be one of 10 known strings, right? So you think, an enumerated type. Okay, well, how would you express that in a way that's compatible with JavaScript in the wild? And so the answer turns out to be the sort of the ideal one from type theory, which is that an enumerated type is the co-product of the singleton types of its values.
Yeah.
So if you say, well, each string is its own type, the singleton type of each of those strings, and then take the co-product of that, boom, there's your enumerated type. And that's exactly how TypeScript does it. It kind of has to, because there will be contexts in which JavaScript will be slinging some subset of those strings around, actually in type theory terms, super type of the enumerated type. And you have to narrow the enumerated type to just the subset of those values that make up that particular subset of the values of the enumerated type, blah, 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 if you want to remain safe.
Yeah.
If you don't want it to accept, if you don't want your function to accept any of the other elements that aren't valid in that context. And it's like, okay, that's actually a hard problem. And the TypeScript team solved that problem. Why? Because they had to be backward compatible with JavaScript and the gazillion libraries out there that work that way.
It's interesting how we've seen a lot of the evolution in mainstream typed languages with TypeScript and Kotlin is mainly what I'm thinking about. They were so beholden to what they were building on top of.
Right.
In the case of Kotlin, mostly the JVM. In the case of TypeScript, JavaScript. And Scala, interestingly, started with Java and JVM stuff as being, one of the core principles. And I don't know if I would totally consider it a core principle anymore. I mean, the interoperability is still there, but it's
interoperability in Scala was, Kotlin's interoperability is seamless with Java. It's so nice.
But I think you have to make some trade-offs.
You do.
In what the type system can do.
And they did. Whereas I think Scala, I don't know if Scala 3, it feels like, you can do it with work, but that's not what we're about.
Yeah.
And I appreciate that.
Yeah, I think that's true and fair. I haven't talked specifically about the design of Scala with Martin for a very long time, but looking back, I think he had some pretty trenchant and ultimately maybe even regretful things to say about the design of existential types in Scala, which are designed the way they are, if memory serves me correctly, for the sake of compatibility with Java generics, which he also designed. I think one of the things that I think a lot of people in your audience might not know is that Martin was directly involved in the design of Java generics back in the Java 5 days, and I think he wrote
penance for that.
But he's
I got to make this right.
But
then
exactly.
he still wanted to be compatible with Java, so then he probably couldn't do everything he maybe wanted to do with the types.
Well, and rightly so, I have to say. I don't think Scala would be even as successful as it is, and obviously it's still a niche language, to be fair and honest. But I don't think it would even be where it is if he hadn't paid so much attention to that compatibility. And if you go back, and I sometimes do, just for I don't know, nostalgia, I suppose. But he did a presentation, Google Tech Talk, back in, I want to say 2006. if you can believe that. About the Scala experiment was the title of that presentation.
I'll have to look that up.
Yeah, I do believe it's on YouTube these days. And he talks about that explicitly, of course, as you might imagine, in 2006, and to a Google Tech Talk audience. But sort of, why build on the JVM? Why and what were some of the design decisions that he made that were motivated that way? And this is coming after, I don't know if you guys know this aspect of the history either, but he had designed a couple of experimental languages before that. Pizza was one of them, and Funnel was the other, and they had some really interesting concurrency features. But he learned what he wanted to learn from them, I think, which was that some of the design choices there didn't work at scale, and so Scala really, in my mind at least, again, I'm at risk of putting words in Martin's mouth, but came out of the results of Pizza and Funnel, and really wanting to, first of all, drive mainstream adoption, and secondly, support certain idioms and paradigms well, but not with the kind of fine granularity that Pizza or Funnel did.
Yeah, it's interesting to see how, even though we'd like to leap forward into, really super pure languages, mm-hmm. we have to accommodate what a certain percentage of people understand now. Yeah. And the whole industry has been that kind of progress. Okay, everybody understands what generics are. Well, not everybody, but enough people understand what generics are that we can do this now, and then we can do that.
Well, you kind of wonder how many languages have to be designed without generics and then bolt them on very painfully later. I mean, let's see. So C++, Java, Go, it's if there's one thing I would offer to prospective language designers today, it's that you need parametric polymorphism out the gate. It is just so unbelievably excruciating to add later.
Oh, yes. And I don't know if you know the story, but when Gosling was designing Java, it was, who was one of the guys who started Sun initially? He lives in Aspen over here.
Bill Joy.
Bill Joy, thank you. Yeah, because there's an interview with him on Artima, and he talks about how he really tried to get Gosling to add generics from the beginning. Gosling said, "Nah, we're in a hurry. We can't do that."
Right. And yeah. So, we don't have time to do it right.
So now we've been paying the price of that.
Oh yeah.
Yeah. Which, and to be fair, if you're not starting from the perspective of, I want to say standard ML was the first language to really have parametric polymorphism baked in from day one. So unless you're willing to start from the ML perspective, which the Java team certainly was not, the C++ team was certainly not, the Go team was absolutely, most definitely not, then it's a defensible claim that it's too complicated to do in the context of a language that isn't contemplating it from the outset. In other words, almost by definition, a language is not in the ML family. It's not standard ML. It's not OCaml. It's not Haskell. It's not Scala. You almost wind up making much broader design commitments, I think, if you start from the perspective of, of course we need parametric polymorphism. I'll go ahead and argue that is the case. You do need parametric polymorphism. So your language is going to be in the ML family. I think
that's the ML family one way or the other.
One way or the other, yeah, by hook or by crook. I mean, it almost does feel that way. It feels like C++ got dragged over, so much so that it bifurcated that community, right? I mean,
Well, at the time, I was on the committee when that was happening. And, and it was, the argument that Strustrup made was, we're going to break some code, but the amount of code that's out there now is basically minuscule compared to
now's the time to do it.
Now's the time to do it. And And there are decisions in C++ templates that I find superior to some of the other parametric polymorphism approaches.
Yeah, I was one of those people who wound up on one of the sides of that bitter divide. Back when it was C with classes versus Boost architecture astronauts. So I was absolutely on the Boost architecture astronaut side, and I agree. I think the unfortunate thing about C++ templates, in my mind, is something that Tim Sweeney pointed out a long time ago. Speaking of people you should have on your podcast, he pointed out that it's just bizarre that you have this Turing complete type level programming system kind of grafted onto C++, but it's so syntactically constrained, and the only types you have at the template level are integers and booleans. So you wind up having to build up anything at all interesting almost from by induction from first principles. You're creating all these recursive template types and the curiously recurring template pattern and all that kind of.
Never completely. No, it always confused me.
Yeah, of course, it is confusing, and it works. It's confusing, but it works, and I think that's the tragic description that Tim was pointing out, is that you can build this stuff. You have the computational power. It is Turing complete, which so the template language of C++ is a Turing complete programming language. It's just so primitive and ugly syntactically and semantically. And
but it's backwards
it
compatible with C.
It's backwards compatible with C.
You can take my C code and run it on C++.
Right. Well, and that gets us to another important topic that I do want to touch on. So I was just listening to some of your previous conversations, and of course your wonderful conversation with our good friend Dick Wall. And you guys talked a little bit about, can we have safe and efficient? Why do we have to choose?
Yeah.
And
are we always going to make trade-offs between safe and efficient?
And I think let's talk about Rust for a minute. So, Rust also came out of the C++ tradition, if you will, right? And here's Mozilla with this enormous C++ code base, and they're experiencing all the pain of manual memory management and all that kind of stuff. So they're like, well, let's solve that problem. And the way that they go about solving that problem is to introduce a very particular kind of type system, an affine type system.
What's the name again?
Affine, AFFINE. It's not quite a complete linear type system. It's an affine type system. And the idea is that now in your type system, you can say things like, this resource is only used once and is guaranteed to be relinquished, after and the type system guarantees that now.
Yeah. So you've moved some idea of resources into the actual type system.
Into the type system, yeah. In an even more powerful way than Haskell or the CATS ecosystems, types that support what essentially amounts to elevating, try catch to the type level in some sense. You can still violate those guarantees. Whereas in Rust, if you violate the borrow checker, dude, your code won't compile. Famously, right? I mean, people sort of beat their heads against the borrow checker for a while until it starts to make sense to them. So in that sense, it's a lot like the conversation about monads. What's a monad? Well, I'm not going to bother trying to explain it to you. Just do this until it makes sense.
Yeah. Borrow checker thing.
Yeah. And the borrow checker in Rust is the same way. But the point is, there you're starting to see the evolution of the type system to account for things that have historically been low-level concerns, have been to some extent efficiency concerns, and it's compiling to native code, and it's so it is definitely performance focused. And so here's one step towards that safety and efficiency, having our cake and eating it too. The cost in my mind with respect to that compared to a Scala or a Haskell or an OCaml is that we don't yet know how to combine some of the features of, say, Haskell's type system with this affine type discipline, or better yet, linear type discipline. I can't wait until we get there. I hope we do.
Do
From
you
the
know if
perspective,
Unison has done anything around trying to combine these as well?
if who has, sorry?
Unison, the Unison language.
Unison. Oh yeah, good question. So our friend Runar and Paul Chiasano and Stu O'Connor and crew. Good question. I don't yet understand Unison well enough to answer it. I do know that they're
Yeah, you and
taking.
have Renar, Paul are both on.
Yeah, I'm going to leave you with a list of people to have on.
Yeah.
So they're doing an algebraic effect system, so that immediately puts them outside my ken. I'm aware of the research that's being done on algebraic effect systems. Um, so another name to put on your list is Oleg Kiselyov, who also has presented at Strange Loop. And going back to that very briefly, I made it clear to the organizers of Strange Loop when Amanda and Oleg and I were there that if they scheduled our presentation, Amanda's and my presentation, at the same time as Oleg's, I would be missing my own presentation. So just so you know, so yeah, have Oleg on. But and why did Oleg come up? Oh yeah, algebraic effect systems. So he's written about that on his site to some extent. There's some interesting Microsoft research about that, and then there's Unison. Gosh, does Unison implement anything like
resource
yeah,
deallocation kind of?
Yeah, I think the answer is yes. I mean, they certainly are concerned about resource safety, especially since they're very, very focused on distributed computing and almost like heading back towards the research on mobile code and things like that. I don't know. That's a good question. That's a good question to take to Runar and Paul and Stu.
They certainly covered it in their book. That was one of the primary examples.
Yeah.
Resource management. Yeah, I mean it's something we all struggle with. C++ is not alone in that regard, and it's funny how I would say 50% of what I try to share when I talk about purely functional programming on the job in Scala is here's how you do that in cats. Here's resource. Here's bracket. I don't know why I had so much trouble remembering that. But was sort of, so the interesting thing is not only does it formalize the notion of try catch as a type, but also, hey, the whole point of typed functional programming is there's an algebra around it now, so you can actually reason algebraically about your resource management, which ultimately is the point. And I guess I want to dwell on that for a little bit too. Why typed functional programming? And this gets us into the differentiation in my mind between the CATS ecosystem and the Zio ecosystem. Excuse me. So my good friend John DeGoes and his team have done a great job making purely functional programming Scala native with Zio. I mean, let's just acknowledge that up front. Plays better with type inference. Is more concrete. I know you and Dick Wall talked a fair amount about the value, or actually, no, going back to Kit Lanking.
Yeah, with Kit.
Yeah. Talking about the value of concretization. Trying to avoid over abstraction. That's all good stuff. What I don't know yet, and I know there's an answer, I just don't know what it is how the Zio ecosystem represents certain named abstractions and their algebraic laws. So for example, I don't know what the Zio thing. I don't know what the name of the Zio thing is. That is a thing you can use in four comprehensions. Now,
have you looked at Prelude, the Zio Prelude stuff?
Yeah, I know that's underway, and I know
I don't know yet how Prelude impacts.
Yeah,
will eventually impact Zio. Like,
right.
Do use type classes from Prelude to indicate that this thing is a monad or this thing is a full.
Especially given that the ZO ecosystem is all about avoiding type classes, right?
Yeah.
So I'm like, I mean, when I heard that first from John, I'm like, okay, I'm skeptical, John, and then he did that great presentation. If you haven't seen it, I recommend it.
We did
Programming without type classes, right?
Yep.
That's the best exposition of the philosophy behind ZO I've seen. But he makes commitments there that I fundamentally disagree with. Avoiding type classes completely, avoiding higher kinded types, and I'm like, gosh, I don't think so. I mean, free structures, that's great. That's absolutely a great launching off point. But one of your free structures had better be a free monad. Otherwise, how do you use a for comprehension? So, and again, I know there are answers to all these questions in the ZO ecosystem. I just don't know what they are.
Yeah,
that's all. And I would love to hear that. So if you could invite John on and have him.
Well, John has been on our list for a long time.
A long time, yeah. So like I said, I'll leave you with a lengthy list of people to bring on. But so I remain in the CATS ecosystem, and I mean, really, really like. It seems fundamental to me. I know that's not really literally true, but it feels fundamental to me to be able to say. Monad square, open square bracket option, close square bracket. But that is admittedly weird. Why is it weird? Because option itself takes a type argument. But I can say monad open square bracket option close square bracket and not say a word about what kind of option I'm talking about. And nevertheless, that is a complete type. Monad bracket option is a complete type. It has an instance. There is a value of that type. And so that's your higher kind of type, of course. And that's a big, I can't disagree with the folks who point out that that's a big mental leap. It is. And then, okay, how do you get at this monad square bracket option square bracket? Well, you take an implicit argument of that type, and it's like, okay, what does that buy you? Well, you can invoke functions on that implicit argument as if that were the thing you were interested in programming with. And, there's some syntactic enrichment. Sorry, come again. Well, if you have an implicit class that takes the base type that you're interested in, and you can add these methods around it and blah, 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 blah,
it's a little wild. When really what I think you're ultimately trying to do is, like you said earlier, is be able to have some expectations of the algebraic properties of something.
Mm-hmm. Yeah.
And monad is being just a type alias for some combination of algebraic properties. Right. And that's ultimately what we want to be able to do is like, oh, this thing is commutative. This thing is associative. You want to be able to have those expectations on how you interact with it.
And I think ZO does a great job of focusing on those basics. If I remember what John said in that presentation correctly, that or maybe what I saw from ZO Prelude when I looked at it, is that they concentrate on the basics of associativity, commutativity, distributivity. Your really, really basic algebraic properties.
Yeah, that's concerned with lattices and semi-lattices, and
right?
All the other ways that you can combine algebraic properties. They're like, what are the most common algebraic properties that we'll use? And
so those are the basics, and they turn out to be unbelievably general and powerful, and that's awesome. But the reality for me is that I actually rely on the applicative laws all the time. I actually rely on the monad laws all the time. I certainly rely on the monoid laws. I mean, I guess that's, to me, I mentioned, okay, what's the name for the ZO thing that you can use in a for comprehension? Because that's something that your average Scala developer is going to want immediately. But especially as a web programmer, it just seems like I'm always combining things that can be empty, and so that's a monoid. And the CATS ecosystem has just a staggering number of really cool and useful, not just cool, pieces of functionality that are based on the idea, well, in particular, the combination of applicatives and monoids. So like fold map A, apply some function that returns a type that has an applicative instance across all the members of a foldable. And then if the result of that applicative has a monoid instance, you can combine them all in one go. So I think of, in particular, parfold map A. So do it in parallel. I call that spark in a box.
Yeah,
you know,
spark in a box.
Because that's what it does. It in parallel applies a function that returns an applicative of some type that has a monoid instance and combines it at each step as each result comes in from the concurrent operation.
It's just
And that
in
completely
Spark you can
violates.
easily foot gun yourself because you don't have the same guarantees of
Yeah,
type system.
it's all Java and Hadoop based, and now we're back to Java just not really having a good enough type system to tell to say what you want. I don't know. But that's a good example of something parfold map A, and John would say, understandably, again, I'm not trying to be critical, but he'll say use domain specific language, don't use abstract language, and I'm like, yeah, but here's an example of some abstract language that turns out to be just ridiculously useful. It was like, all right, I'm anxious to hear, I guess is the way I would put it, what the alternative is. And you know what? It could take years to get there. It's a lot to say we're not going to stick with the Haskell type class tradition. We're not going to continue to use these names. They're too weird and abstract. We're not going to continue to rely on these algebraic laws. Maybe there's another set of algebraic laws that we can build around these free structures and do it from scratch, do it from the ground up. So it's Scala native and it is purely functional programming in Scala for Scala, and is not bound by this history. That's a noble goal and a worthwhile goal. I absolutely support that. I just don't know how to use it myself today, given that I want the relationships that I get from the classical type classes.
Yeah. Well, and it'll be interesting to see how Scala 3 has some impact on some of this as well.
Mm-hmm.
And maybe that's because of the revamped type classes or better ADT support or whatever it may be. It'll be interesting.
Union types, yeah. The big that was such a shock to me when Scala first came out. Actually, that Scala 2 didn't have proper sum type, a proper coproduct type. Yeah, that's such a great advance in Scala 3. In my mind, probably the biggest, because heaven knows I'm constantly wanting to say this type or that type or some other type, as I think Dick pointed out, we encode that all the time with a sealed trait hierarchy and inheriting case classes, and it's like,
Just
so
too much syntactic overhead.
So would you say that's a kind of polymorphism?
Well, yes, because you're representing a sum type, which means you don't know the exact type statically that you're interested in. But so I mentioned earlier TypeScript and its support for enumerated types as a kind of a special case of this idea, that you can take the coproduct of the singleton types of the members of the enumerated type, and boom, there's your enumerated type. Yeah, it is relevant to polymorphism in the sense that, especially at I/O boundaries, right? A lot of the time at I/O boundaries, you don't know exactly what type you're going to get. It can be one of n different things, and so you want to be able to say, take these bits from the wire and look at some portion of them, look at some discriminator, right? So we know about discriminated unions, and using that discriminator, you now know, okay, it's this type or it's that type or the other type. But how do you express this type, that type, or the other type? Well, that's a sum type or a sealed trait hierarchy in Scala 2 or a union type in Scala 3, or I forget what they're called in other languages, but type theorists take your pick, sum type or coproduct, depending upon how much category theory they've swallowed.
Yeah. Bruce and I have been learning. I feel like we've been kind of taking the next step into our understanding of polymorphism, because I definitely, for a long time, my perspective of polymorphism was that it was just subtyping, and subtyping was the only way to do polymorphism. And now we've been learning about type classes and ad hoc polymorphism, and some of these other ways. Well, and even like beginning to think about about generics or type constructors as a form of polymorphism. I think it was
Right.
probably your talk that really opened my eyes to that.
Pointed in that direction.
Yeah,
Good.
yeah, and all of a sudden seeing like, oh, polymorphism is this much bigger
Yeah.
thing that can be accomplished with different strategies,
Right.
and getting out of the mindset of just subtyping is the only way to do this.
Yeah, and to me, that's kind of the tragedy of object orientation, really, at the end of the day. And you know, we've all, this has been well rehearsed at this point, so I almost feel bad about sort of revisiting it. But you know, even long ago, over a decade ago now, Alan Kay was saying things like, hey, I invented object oriented programming, and C++ was not what I had in mind. And going generalizing that, I would say. I think he made the point explicitly at least once that people took the inspiration from Smalltalk as he conceived of it and focused almost entirely on the class-based inheritance thing, when in his mind it was really the late bound message passing thing that was key, to his conception of Smalltalk. And I have a lot of sympathy for that, because heaven knows anybody who's been in the industry as long as we guys have has spent a lot of time with UML and class diagrams and charting out these static inheritance relationships that ultimately in practice in any system of any complexity turn out not to actually express most of what you want to know about the behavior of the system. And especially, I mean, I was a Mac programmer for so long, and guess what object-oriented programming has to say about event handling? Bupkis.
Yeah, yeah.
So these days, I mean, going back to TypeScript, I have a little side project that I've been working on for a while, and I'm not a front end guy, which is good news, bad news. It meant that I sort of had a lot of freedom, and the freedom born of ignorance, right? To delve into the available
We like
tools.
to call it beginner's mind.
Beginner is exactly beginner's mind. The one thing I went into it sort of knowing by the time I started this was, well, I'm going to use React, right? I mean, it's just kind of clearly one, in the JavaScript framework space.
Yeah,
but I wanted
the winner is clearly the best one.
Well,
it's Elm, huh?
Yeah. No, I didn't, and I mean that's a whole sidebar that we should take up another time. But I knew I wanted a functional reactive programming framework of some kind. So, and I wanted to use React for mainstream learning resources and so on and so forth. So I found Cycle.js, and I found a set of design elements or design system for React that Microsoft did. Actually, they use in Office 365 and all that sort of thing. So I found a couple articles. There's a great blog post from the Cycle.js developer about using React with Cycle.js, and then basically I found all the tooling to crank all of the purely functional thing in TypeScript to 11. Nice. And to the point where it's like vars, no; classes, no; nulls, no; et cetera, et cetera, et cetera. And it turns out this actually works. This actually works fine. The combination of Cycle.js, TypeScript, React, Microsoft's design system, and
some functional,
I guess, ESLint and some settings to say disable this, disable this, disable this, disable this,
and
it works.
It's
it
a
works.
pretty good happy path.
It's yes, right. And by the way, I thank you for reminding me. If you haven't seen my my LambdaConf 2018 keynote, please do sometime. But in it, I explicitly say that one of the things I like about typed functional programming is that it lets you just code the happy path.
Yeah. Awesome.
Because monads are fail fast, right? So you just not accumulate, but you cascade your errors down the monad composition. Or
hey, can I insert a question here, because it's something I've been trying to figure out
please.
for the book, which is, so error monads capture things that we would normally have done with exceptions.
Right.
And then at some later point, we do the equivalent of the catch clause.
Mm-hmm.
But what else is superior between, monads versus or not checked acceptance, just exceptions?
The
I mean,
exceptions in general. Yeah.
yeah.
Um, so, I mean, it's an answer that might not be satisfactory to a lot of people. It's one of those things that if you're not already on this side of the river, may not sound all that compelling. But it is once again the algebraic reasoning that you can. So not only is there the monad type class, but there's the monad error type class, and honestly, it almost seems to me that that's the one we should talk about first. Like, monads are awesome, but not all monads are failure monads. And monad error is the type class that represents the ones that are. So there are operations on monad error that are not on monad, on just plain old monad. So, for example, since I'm a cats guy, the monad error type class in cats gives you the ability, for example, to say, please surface whatever the error is as a value in the monadic context without escaping the monadic context. So if you have an f of a and you say the method on the monad error instance is attempt. So if you say attempt on that, then instead of an f of a, you have an f of either whatever the error type is in a. But it's still in the f context, whatever the monad error, whatever the type that has a monad error instance is. So now you can map over that. You can do whatever you want with that either, and so on and so forth. Conversely, there's, going the other direction, there's rethrow. So if you have an either, you can collapse it into the monad error context and just act as if you just had an A in
You
this.
can go in and out of left and right. You can go down to a value and then come back out to a left and right structure.
Right. Yep. So you can either you can surface the failure in the monadic context, or you can unsurface the failure in the monadic context, and stay in the monadic context, which means the monad laws are still satisfied. There are some monad error laws that are unique to monad error that are also satisfied. So you get all the benefits of, and here's where John DeGoes and I strongly agree. I would say most strongly agree. We agree on a lot of things. That the name of the game is programming with values. Everything is a value. Your obviously your values are values. Functions are first class values. Errors are values. The idea or the representation of concurrency is a value. And so when you have values, then you can use the type system to impose these algebraic laws. And to me, that's the whole point. It's not even that I do. Like if you were to ask me right now, hey, Paul, what are the profunctor laws? There is absolutely no way on earth I would be able to tell you. The point isn't to memorize the laws. The point isn't to sort of sit there and dogmatically say, yes, let me replace this expression with its value and, the substitution model of evaluation and does this satisfy these laws and all that kind of stuff. I never do that to a first approximation. Not literally never. But, it's not a daily, weekly, or even monthly practice. The fact that I could add a dependency on the cat's discipline and laws libraries or modules and say, you know what, I'm in a weird situation where I've got to write my own monad instance or some more complex concurrent effect or whatever. I've got to write my own instance of this type class. Boy, I'd better check those laws. I'd better make sure that run those tests. The test framework is there. The laws are there.
That's cool.
I could do that.
So,
I haven't had to.
But presumably, the cat's built-in things have all used that to verify
Exactly.
the validity.
Yeah,
so
exactly.
Even so, as a user, you don't have to. One, you can just trust that the laws have been validated.
Right.
And two, you can have expectations around behavior, and this probably is ultimately around composability. You're combining values in a lot of
Absolutely.
different ways,
Yep.
and you learn from the laws. Oh, these things will compose in this way
Yeah.
because of these laws, and now I can make expectation. I can have expectations on this thing that are
That's right.
reliable.
So to
Yeah.
kind of summarize, it sounds like when you do it, say the monadic way, you can reason about it more easily, and then you have all the algebra that can be applied to
Right.
the
Right.
result. Whereas
And
if you do it with a try catch, you're just hurling it over to some other place where you can combine your.
Anything is valid.
Mhm.
take throw literally, guys.
Mm.
When I see a throw in a code base, I think, I get this visual of a catapult. It's like it's like the orcs are attacking Minas Tirith. It's like they're lobbing stones at the walls. It's just and it's so funny
And
too
putting
because
anything they want in the
and
catapult.
putting anything they want in the catapult. And it's
There's a cow.
funny
Wasn't that
because
on
yeah, exactly, Monty
Monty
Python. Yeah,
wants the cow
exactly.
over?
Right.
You
Yeah,
never know what you're going to get with exceptions. You could get a
yeah,
cow. You could get
that's right.
a
That's right.
ball.
Yeah, the technical term for this is dynamic non-local exit, which is every bit as horrifying as it sounds. Um, and why does this come about? One of the other things that I guess is a little frustrating to me as a professional developer and computer scientist is that we don't really talk much about the historical evolution of these ideas. So where did exceptions come from? Well, they came from a history in which you used to indicate failure by returning some magic value, right? And -1 to indicate that something failed or whatever. The problem with that, of course, is that -1 may be a perfectly good value for some function to return. There may not be any spare values in the return type that you can sort of use as a magic value. But that's assuming that you can only return one value. That's assuming that you don't have some types, that you don't have either, where you can communicate the fact that you either succeeded and got a value whose domain can be infinitely large, or you got an error whose domain can also be infinitely large. How many subtypes of throwable are there? As many as you want, more than you want, I would say. So, again, going back to this whole machine-oriented history, that we had C and we had Pascal, and from that came a lot of implicit mindset that there was no way to return more than one value. There was no way to indicate or a type that was either this or that. And it's just sad because that didn't actually last that long. ML, not standard ML yet, but if memory serves me correctly, the first ML hit the streets in 1975. Standard ML, I think maybe the late 70s, early 80s. OCaml was well established by the mid 80s at the very least.
Well, and if you look at mutability itself, that was a way to save memory, which we had to do in the early days.
Yeah. Again, to be fair, when CPU and memory was at a premium, gosh, a portable assembly language like C was just a huge advance. A huge advance. Think about the opportunities that came out of the widespread distribution of Unix and C through the university system. In the 1960s and 1970s, and this would run. You could run these early Unices with their C compilers and whatever applications, quote unquote, were available. You could run them on your PDP-8. Maybe your PDP-11, right? I mean, pre-Vax.
Like what?
8K?
8K of memory?
Yeah, right.
Yeah. And then
Right.
Can't anything in 8K of memory anymore.
Well,
you can't fit your stack in 8K of memory today.
My study of organizational structures, the thing that has come out for me is because we look at an organizational structure and we go, oh, that's terrible. I mean, the feudal system, oh, that was awful.
Right. Right.
but it was better than the thing that came before it. Each
That's right.
one, and then you use it for a while and you go, oh, well, here are these other problems. And then you come
Right.
up with a new structure.
That's right. Yeah, the tendency to project modern values on history is called Whig history, WHIG, and is frowned upon in professional historical circles, as it should be. But we do it in technology all the time.
Yeah.
All the time. And I'm
What
guilty
were
of it.
they thinking?
Yeah. What were they thinking? But there are inflection points. So, high resolution bitmap displays, mice, fancy user interfaces. I mean, now we're talking about the Lisp machines at MIT also in the 1970s, and attempted to be commercialized famously and famously unsuccessfully by Xerox in the 1980s, right? So they had Smalltalk machines and Lisp machines and all this kind of stuff. Symbolics had their Lisp machines. Texas Instruments had their Lisp machines. So there was a lot of innovation that happened relatively early, but I do tend to agree with folks who say, well, those systems tended to be unsuccessful because they were expensive and resource hogs, and then Smalltalk and Lisp added on top of that the whole image-based system where you couldn't just compile things down to a nice little binary and ship it to somebody, so that was problematic. So these were very developer oriented. It's like, nice. So somebody's trying to create a really awesome developer experience and largely successfully. And this brings me back to the fact that I know one person you should invite on, Tim Sweeney, CEO of Epic Games. I mean, the Unreal Engine, to me, is the modern developer focused system, because you can program to the Unreal Engine in C++ if you want to go hardcore. But by the way, it does incremental compilation and linking, and you can do this while you're editing your title in Unreal Ed, the Unreal Editor, while it's running. And you can make a change to your C++ source code and say save, and about 4 seconds later, that change will be effective in the code that you're running while you're running it. But you don't even have to do that. He's got a visual programming system called Blueprints, that is basically a data flow graph system that entire titles are written with for game developers who don't know C++. And so there's a very successful example of a very powerful visual programming language that's used for high performance. People develop real-time games with it, and it's for real. And Tim has lots of interesting thoughts about programming language design and the future of technology generally, and the metaverse and so on and so
forth. Well,
I
think you mentioned him in both of the presentations that I watched.
I did. Yeah. I'm a fan. I'm a fan of Tim's. Tim's an acquaintance down here in North Carolina. He was kind enough to invite me to dinner one time some months after I moved into the state. Really nice guy, brilliant guy, and just has had a lot of really sharp things to say. Most of the stuff you saw in those presentations, he said publicly on Lambda the Ultimate, just a very careful, thoughtful. Think about the position he's in, where he's got hundreds of licensees, if not thousands of licensees of the Unreal Engine, developing titles. They've got teams of programmers ranging in size from 5 to 50 or more. He's sub-licensed the Unreal Engine to Sony and Microsoft. So, it almost is like job one for him is to reduce support costs for developers using the Unreal Engine. How do you do that? Well, you make everything you make the right thing the easy thing. You just have to very aggressively make the right thing the easy thing. And I think that's part of his genius is that, he's done that to such a great extent with the Unreal Engine. He's designed a dependently typed programming language with a couple of colleagues from Intel. That hasn't been publicly released, but, it's indicative of the sorts of things that that he thinks about. And it's fascinating to me that somebody whose focus has to be, this has to be dirt simple for developers. This has to be dirt simple for artists. Level designers have to be able to make progress independently. They can't be blocked on waiting for their C++ developer to do X. They have to be able to make progress on their own. And so what's the answer to that? Possibly some dependently typed programming language. There's a point at which the question becomes, how much generality does it take? How much abstraction and generality does it take before it magically crosses some complexity and difficulty line and comes back around almost full circle to, well, of course it works this way. How else would it work?
Yeah. One of my burning questions, I think kind of related to this, that Bruce and I have talked about a lot, but I want to hear your perspective on is, I think that we are in such a bad place with declarative languages. And they're just always like, oh, this is simple, but then, you get down the path with it and it turns out it's no longer simple and it just is a total disaster. And the tooling
right.
that was promised around the declarative language was never built, and so on and so forth. Like,
right.
What does the future look like with declarative languages? And
it's a super great question.
So I was thinking about this based on your with Unreal and having the Flow Designer tool. Because to me that the way that we would typically think about that today is, oh, so that must be writing some declarative language that then gets parsed and run underneath the cover.
But it is. Yeah, and it is. So what Tim did many, many years ago, back in the 90s when he was doing the first Unreal Engine, was he came up with a really good, powerful, extensible reflection system for C++ because he needed to implement a scripting language for the engine that was Unreal Script back in those days and through Unreal Engine 3. And Unreal Script needed to be able to invoke methods on C++ objects, and C++ objects needed to be able to run game scripts, and So he needed this reflection system for C++, which he wrote as part of the Unreal Engine. So fast forward to, I think, Unreal Engine 3, if memory serves me correctly, was where Blueprints, or used to be called Kismet, first showed up. And it absolutely relies on that reflection system to interact with C++ objects in the engine. And so, what does the flow system actually do? I don't know for sure the answer to that question. In Unreal Engine 4, I can tell you two things. One is that it's possible to compile your blueprint to C++. So there is a possible, there's an ahead of time compilation process that you can take advantage of for performance reasons. So that does tend to support the idea that the blueprint is basically just, quote unquote, just a graphical abstraction on top of C++. But that can't be completely true, because Blueprints also participates in this live coding thing that you can do in Unreal Ed. So you can develop a graph, you can make some material changes, art changes, code changes elsewhere, etc., and you can actually run. You can say run the game, and then you can actually follow the changes of the data as they flow through the blueprint visually. Those get rendered. I'll send you guys a link to the tech demo that one of their lead designers did way back whenever it was that Unreal Engine 4 first came out. But I also think that I know what the theoretical underpinnings of the blueprint system are, because it was Tim who pointed me to a really interesting paper on the lambda calculus with LetRec. and it's like, oh, wow, that's amazing. I had no idea. And it's like, so it's a window into Tim's brain and maybe points in some directions to some answers about how this works. But let me back up to your more general question about declarative programming. the big challenge that declarative programming has historically had is effects. Right? It's how do you do I/O and Prolog? Um, and so at some point, I think there's an intersection of purely functional programming and whether it's logic programming or concurrent constraint programming. I think there is a future direction that we can look at and say, yeah, something is going to subsume these. Something is going to make it possible to say, to achieve that Prolog dream, right? Of you say what you want instead of how you want it to be done. And that includes interacting with the outside world monadically or, algebraic effects or whatever it is. We don't know yet. But those things will get married at some point, and there will be an answer. I'm confident of that. I don't think it's something that we can look for in the next 5 years, but I do think that direction is clear.
Yeah, it does seem so. Awesome. Anything else, Bruce?
No. If I hadn't just finished reading the Red Book,
which is a great book.
It is, and I understood maybe a third, but I got through to the end,
which is better than most people do.
Have been able to keep up with this conversation.
So, yeah.
And sorry.
No, that's fine.
That's I feel like I'm just beginning to grasp some of the ideas from your presentation, your first strange loop presentation.
Types versus tests.
So I'm just now getting there, how many years later. So your wisdom and leading us on a journey that many years from now I will understand some of this podcast.
Well, and let me maybe close with that observation. I structure these presentations in a very specific way, and I don't even know if I've shared this with Amanda. I think I have, but it's important to me to talk about things that were true before I was born and will continue to be true long after I'm gone. So, talking about the lambda calculus, talking about type theory, talking about category theory. At the end of the day, what I'm urging the industry to do is to go back to the foundations. The Turing machine is only one model of computation, guys. There's this other one called the lambda calculus, and when you add types to that, you get the various kinds of typed lambda calculi. So, by the way, for the critics, if you have a problem with doing typed functional programming, your argument's not with me, it's with Bertrand Russell. So take it up with him. But each presentation I've done, I've had that goal. I've had the goal of repeating something, not saying anything original at all. Repeating something that was true before I got there and will be true after I'm gone. And the other thing I try to do is in each successive presentation, I try to elaborate on some point that was made in a previous one. And you can see that very clearly in types versus tests and type systems, the good, the bad, and the ugly. In types versus tests, Amanda and I tried to lay down some ideas as to how you might choose when to try to use the type system that you have and when you should rely on tests. And then, one of the things that immediately comes out of that is, well, is your type system any good? And that leads directly to type systems, the good, the bad, and the ugly. So there's a through line that I try to maintain. And I don't know how successful I am.
Was your 2019 presentation yet another?
The LambdaConf 2018 LambdaConf keynote. That was on one hand, yes, there's material in there that if you were to ask, okay, how does that relate to formal logic undressed at Scholar World 2015? I could come up with an answer to that question. But the LambdaConf keynote, I was a little more self-conscious about the fact that it was a keynote, and also maybe even a little, maybe not defensive, but it was, typed FP on the job, why bother? So I was more aware of the need to address industrial considerations, than theoretical ones. Almost everything else that I've talked about has been very theoretical. But I like to live at the intersection of theory and practice. which is why I work in Scala and purely functional programming in Scala.
I mean, it's kind of a definition of computer science, isn't it?
Right.
Living at the intersection of theory and practice.
Yeah, hopefully.
Yeah, and there are more intersections to drive towards. So I said I was going to leave you with that last observation, but let me make one more, and then I'll quit bending your guys and your audience's ear. We have to think about green computing, and this is another subject that you should raise with Amanda. So when you look at the intersection of physics and computing, it gets really, really, really interesting, and believe it or not, relates to purely functional programming. So back in the 60s, a researcher determined I think it was the lower bound, if I remember correctly, of the heat dissipation that must accrue from flipping a bit in memory. Like there's a lower bound on how much waste heat must be emitted by flipping a bit in memory. And this is a direct consequence of quantum mechanics, because of the 5 or 6 or 7 different quantum mechanical theories, they agree on one thing, which is that information is never lost in the universe. It's called the unitarity principle. When Schrodinger's wave collapses, something happens. Something is guaranteed to happen. Probability 1. And so it's like, okay, great. So if you flip a bit in memory, by definition, it's like, that sounds like information must be lost, right? Whatever the old value of that bit was is now lost. No, it's not. It's propagated out to the universe as waste heat. And so you can compute the lower bound on that. If you could make computing reversible, if you could make it so that bit flip didn't actually lose the old value, but somehow that old value got propagated, if you could make the hardware immutable, if you can make the hardware reversible, we talk about reversible computing in certain research circles. If you had reversible computing hardware, then you could eliminate the heat loss, because the information wouldn't be lost to the physical environment. The information would still be in some other bit somewhere else in the system. Now, of course, you can't extend that infinitely, as far as I know. But think about that for a while. Think about the idea that as your laptop gets hot on your lap, when you're reading too many emails or watching too many videos or playing too many games or what have you, that back in the 60s, somebody figured out what the lower bound on that heat loss is when you flip a bit, and B, taking a purely functional programming approach to hardware may actually help the environment.
Right.
At some point.
We need something beyond the transistor to save the world.
or at least improve it, our little corner of it.
That's right.
To some
the best
degree.
We can hope for.
Yeah, right.
Well, this has been super fun, Paul. I really appreciate your time and your wisdom.
Pleasure's mine.
Sharing it with us. So.
Yeah,
I need to rest my brain now.